I'll present a little bit of our work on X-ray absorption spectroscopy and resonant inelastic X-ray scattering. So the first part of the talk will be more historical, so it will be an introduction to X-ray absorption spectroscopy, which is maybe not new to everybody, but I will try to combine all the different edges in a common interpretational scheme. And then switch to the second part, which is more new from the data point of view, the resonant inelastic X-ray scattering experiment. Okay. So if we do X-ray absorption spectroscopy, we have to solve the Fermi golden rule. So that's the theoretical goal. So what happens with an X-ray? It excites a core electron to empty state, and you have to calculate the transition of the initial state wave function, so the ground state of the system, to the final state wave function, so that's the ground state of the system with the core hole and the extra electron and the empty states. And then by solving that, you can try to interpret the X-ray absorption spectra. Now, X-ray absorption spectra always look like this. So you have two parts of the spectra. You have an exciton, or not, but let's say I mainly discuss transition metals, and then you have an exciton, and then you have the edge transition, which you can calculate. So this will be a general picture which I use for all the edges. I start with oxygen K-edge X-ray absorption. So there are data I took here in Brookhaven 30 years ago. So you will see them later. So if you measure an oxygen K-edge, so the excitation of an oxygen 1s core level to an empty state, there are no excitons. So the core level, the core potential is not strong enough to create excitons, at least not in solids. And you only see band transition. So that simplifies your interpretation a lot. So you do your calculation now with your Fermi golden rule simplifies to essentially the density of states. So what you now have is that the intensity of X-ray absorption corresponds to a matrix element, which also I assume to be constant for the moment, times the density of states. So you see directly in your spectrum the site and symmetry projected densities of states in your X-ray absorption spectrum. So to go to real spectra, so these are the oxygen K edges of transition metal oxides. So you can see they are very old because they are drawn by hand. I didn't have a computer at that time. But this is a calculation without a core hole. But the interesting thing is that this is titanium oxide rutile, and in that case, if you put a core hole, so then I can point that out. So later we did that. So you see that the crystal field splitting is a little bit too large in the calculations, and if you put a core hole, that exactly fixed, so you get really the correct splitting between the T2G and E2 states. What happens if you put a full core hole? Then the intensity of the first peak drops. So you get a better description of your peak positions with the core hole, but the intensity, the overall agreement with the experiment goes down, and you can only solve that. I think it has only been recently solved by David Prendergast's calculations, where he does because you should not put a full core hole. You should fit your core hole potential to the final state. And if you do that, then you get a complete description. So the really detailed, accurate description is much more complicated, but you get 90% of the ground state density of states. Okay, so that's the case for transition metal. For the ligand edges in transition metals. Now I switch to the metal edges, and then we get exactly opposite picture. So everything is excitons. There is an edge jump, so I should not cross it out, but it's so small that you don't see it, and it's never analyzed, as far as I know, in any paper. So we only look at excitons and no edge jumps. So you get a spectrum like this. So your exciton is not a single peak, but for manganese oxide, it's a few thousand peaks. So this is I'm now in 1990. So actually, the data was taken exactly 30 years ago. Here, I mean at NSLS-I, the Dragon monochromator. and the calculation, we did this before. Just a historical note, so I did this calculation, which is the solid line, before I did experiments. Before I did, in my undergraduate I only did calculations. And then I was at the conference and I saw this top spectrum and I thought, oh, that's nice, somebody else is doing the same calculations. But that was the first spectrum of CT channel on the Dragon monochromate. And the agreement is really perfect, almost perfect. The difference is that the experimental spectrum is saturated, because even electron yield saturates on manganese oxide. So if you desaturate it, if you make this peak larger, you get an almost perfect calculation.
Sorry, you mean saturated experimentally, not in the actual emission process?
Yeah, the actual emission process.
Oh, oh.
Yeah. So because the penetration depth at the peak position here is only 10 nanometers of the X-ray.
So it's a dynamical effect inside the material.
Yeah. So it's the electron yield which saturates. So normally only fluorescence yield saturates, but in manganese oxide also the electron yield saturates.
Have you tried to calculate that?
Yeah, recently we calculated that for, yes. We didn't discuss that if you, yes. You can actually measure it by doing angular dependent measurements and get a lot of things. So you get a perfect fit of the experiment, but that is very surprising because this calculation is extremely simple. So what I do is I say my ground state is D5, and I make a core hole, I put the core hole in 2p, and I put the electron in 3D, and then I calculate this state and that state, and I calculate all the transitions from there to there. But if you approximate your system as D5, you neglect everything. You neglect chemical bonding, you neglect, and still you can explain your experimental spectrum in great detail. So that was the surprising part, that actually this works. And the reason it works is that it's a completely self-screened experiment. When you excite a 2p electron to a 3d electron, the 3d electron is still localized. So everything around the manganese doesn't even notice that something is happening. So it's really a local excitonic transition. I'm going to discuss that now a little bit more in detail because that comes back for the K-edges, metal K-edges. The description we use for transition metal oxides is to use different configurations. So we start off with the ionic configuration. So we say manganese 2 plus is 3d5, and then we mix with a second configuration where we move an electron from the oxygen 2p valence band to the 3d band. So then it's 3d6 leak control, and this has a certain excitation energy. It's not exactly the band gap, but because it's modified by correlation effects. But the charge transfer energy related to that state. And now you can make all kind of excitations. So you can do metal-metal charge transfer, ligand metal, and metal ligand, and make a total ground state. If you do that, then it turns out that only these two are important for X-ray absorption. The other ones they not give a visible effect. So we now end up with a problem where we have D5 and D6 leak control. That looks like a 2x2 problem, but actually is. This is a multiplet of a few hundred states, and this also a few hundred states. And so it's not 2x2, but it's a big calculation. That's a bit difficult to see for manganese, so I switch quickly to nickel to show that. So what you calculate for the ground state is this. This is the D8. These are the energies of D8. So the Tanabe-Sugano diagram for chemists of a D8 system. So the ground state is triplet A2 for D8. And these are all the possible electronic, multi-electronic excitations. And these states mix with D9 leak control. So these are the D9 leak control states. This is delta is 10, so then it's very far apart, and the ground state is pure D8. So that's so nickel oxide is actually here, so at delta is 3. So then you see that your multiplets are a little bit compressed already. So these are the multiplets we see in RIXS later. These are the optical excitations. And you see your charge transfer states relatively close in energy. So an optical spectrum will show the excitations of the ground state to all these excitations, and then the charge transfer. If you go from nickel 2 to copper 3, you go to negative delta. So this is the copper 3 and high PCF superconductors. So delta is -1, and then your ground state is now really a mixture between D8 and D9. You can tell, so it's almost a 50-50 mixture of the states. So with this two configuration model, you can describe transition metal systems accurately, and then describe all the possible experiments you would like to do with them. And then the two nice experiments to compare are X-ray absorption and photoemission. This is the ground state, D5, D6 decontrol. This is X-ray absorption, D6, D7 decontrol. If you work out the energetics, you see that the energy ordering of the two states is exactly the same in the final state than in the initial state. So the process of X-ray absorption is self-screened. So you can, in first approximation, neglect this and neglect that, and then you get still a good description. So that's the case for all neutral experiments. So X-ray absorption, optics, EPR, they are neutral, so you can do crystal field calculations because you can neglect charge transfer. That's completely different than ionizing experiments like photoemission and Auger, because then you take out an electron from the system, the core hole has to be screened, and the screening is done by moving an electron, an extra d electron there. So now you go from D5 to 2p5 to D5, but now the excited state moves down to by the core hole potential Q, which is 8-9 electron volts, to below the D5, and now you need these two configurations. If you forget about this, you can never describe photoemission. Now actually you need more, so now you need at least 3 configurations, maybe 4, because they are very high in energy there, but they all come down here. So that's the difference between X-ray absorption and photoemission calculation. So the theory is the same, but the states which are needed are completely different.
I want to just ask you to pause for a moment. I was actually kind of processing the self-screening discussion, quietly trying to figure out what's going on. And I guess your main point there really is not that the two distinct configurations don't contribute, but they contribute to a peak that has about the same energy, because the splittings are about the same. This is the essence of your argument?
Yeah. The splitting is the same. Delta is a little bit smaller in the final state because the core hole potential is a bit larger than U, but let's say initially the same.
Pretty similar, right?
And also the coupling is the same. Actually, again, a little bit smaller because of the localization. And if you assume that delta is the same and the coupling is the same, you get a bonding and anti-bonding combination of these two states, and the same ones there. But then mathematically, not 100% of the density goes there and 0% goes there. That's the extreme case. In reality, something like 90% goes to the bonding one and 10. So you have a weak charge transfer satellite, but it's something like 10%.
Right, and it's super close in energy as well, if I understood properly.
Yeah, that depends a little bit on the strength of the coupling, because if the coupling is strong, it can go down.
So it can show up as a shoulder, basically.
Yeah. So that's, and the photoemission is different, so then everything is dominated by screening. So I'll come back to this for hard X-ray K-edges, where this also plays a role. Okay, so that brings me to the total picture of interpreting X-ray absorption. If you have a K-edge, you do a single particle calculation, so essentially density functional plus core hole plus U, and that works fine, and that describes X-ray absorption relatively accurately. More exactly, you have to do a two-particle calculation, so either time-dependent DFT or beta salpeter. This is for valence excitation, but then you make all the possible excitations of a core hole to final state, all the single hole, single electron excitations. That works fine for all closed shell systems, not only K-edges but also L-edges. So this includes titanium oxide, that's a closed shell system. So then you can do this approach. If you have an open shell system, these two models break down. Essentially, if you think about it in the excitation process, because you have many multi-electron excitations. Because if you do a beta salpeter calculation, you do a single hole, single electron. But then if you have an open shell system, you can do 2 holes, 3 holes, 4 holes, and that's not in the BSE calculation. So then you need the multiplet calculations. If you like to do this yourself, so we have a very old code, so it's although I advertise it here, I suggest you not to use this code. Because nowadays there's a much better code. So I'm now advertising for somebody else, but I hope Eli agrees. But Eli programmed the code, so CTM for XRX, it still works very well, and actually I still use it, always. But there are some limitations depending on the specific problem that you calculate. And in the new version of CTM for XCS, that's version 6, we interface to this new code, Quanti. And that code is much more flexible and allows you to do a much larger range of calculations. So you can still use the CTM for XCS interface. I always suggest if you're new to start with that, because then automatically you get the spectrum on the screen in a second. But then if you're going to a problem and you have magnetic fields and electric fields and that kind of things, then you should do it by hand, the calculation, and not use the interface. This brings me to all the interesting developments in the first principle calculations. So if they are theorists, so there's a whole range of developments. I try to group them a little bit together. So for solids, there's band structure multiplet approaches. They're done in, I'll put the cities now, Heidelberg by Maurits Haverkort, Vancouver, Saskatoon these days, by Robert Green, and Vienna by Asushi Ariki, and there's a different interface in Stockholm. So what they essentially do, they do a density functional calculation of the ground state, or dynamical mean field theory, or whatever theory you need for your correlated electron system. Then you have that result, then you take out a cluster in real space from that solid, project your reciprocal space result to the real space by Wannier projection methods, and then in the real space cluster do your multiplet calculation like before. So now instead of parameterized calculations, which I do, you have a first principle route to automatically you get all the calculations. A few exceptions, you have to do some tuning, but in principle you have the calculation. So this is in reciprocal space. You can also do everything in real space. I call that cluster density functional multiplet. That's done by in Kyoto by Ikeno and by two groups in PSI. So this Robin Antoanina, he programmed the multiplet calculations into ADF, Ampersand density functional, and people use that. You can just say, I want the LH, and you have the LH. And they use a cluster DFT. That's not completely ab initio because they need some guiding parameters to tune the calculation. For molecules, there are a lot of restricted active space calculations. They all very similar by Scandinavian groups. And Van Nese in Mulheim has a slightly different, okay, he's not in the audience, completely, but similar approach. So it's a configuration interaction on open shells for the exit. Then if you have closed shells, you can do all the direct extensions of DFT calculations, so time-dependent DFT or beta-solvita or multi-channel multiple scattering, and that works fine for titanium oxide, but breaks down for, it's not perfect for open shell systems. So there's a whole range of routes, yes?
So for the first two, it looked like you end up making a cluster in real space and then doing the calculation.
Yeah.
So is there like a rule of thumb how big a cluster should be for you to get a useful result?
Yeah, in many cases, for X-ray absorption, a single metal is large enough for the cluster. So then it's a single metal and the oxides. Of course, they're not the most interesting systems. But so if you have two metals, that can actually also be two metals in a protein. Then of course it's much more interesting to first principle calculations and do your fitting of your two metal sides. So Maurits Haverkort did the full band structure multiplet calculation on two metal atoms, and then the number of matrix elements was 10 to the power 123. So he has more matrix elements than atoms in the universe to solve the problem for two atoms. So it's really, I mean, you need a big computer to do that. So instead of your laptop, where you can get a result in 1 second, now you need a supercomputer and to get the same result. First principle. Okay. So some applications. So this was all theory. So these are historical examples, but I just want to show them what kind of things you can do now. This is an experiment from Piero Gambardella. We did something like 10 years ago. So it's a copper surface and you put molecules on top. What I want to show now is just, I'm not going into the detail of the system, but they have iron atoms. They are surrounded by 4 oxygens in plane. There's copper below and vacuum above. And then you want to describe that system with multiple calculations. So we did multiple calculations and then solve the different cases. So this is the normal incidence and the grazing incidence. So you can calculate your linear diaphragm. So you get information about the orientation in space of the orbitals. And this is the circular diaphragm at normal incidence. So you also get information on the orientation of your magnetic moment. And then by doing a lot of experiments at different angles, you get the final result on the orbital position. So the initial system is oriented in plane. So this is the iron in between the oxygens. And then if you let it react with oxygen at low temperature, the oxygen absorbs as a molecule, so it's not dissociated. It becomes more octahedral. You can see that the distortion goes down and you get a distorted octahedron. And the magnetic orientation goes out of plane. So you have made a system with a bit size of 1 atom. And that was the... so every atom switches from in plane to out of plane. Which is completely impossible to make in reality, because you have to say then to the oxygen atom, you have to go to that iron and then to that one if you want to use it. But okay, that's another thing. So in Utrecht I'm paid to do catalysis. So one catalysis example, also from some years ago. It's a nanoscale chemical imaging of a working catalyst. So somewhere in the Fischer-Tropsch plant in Qatar from Shell, there's a nanoparticle doing Fischer-Tropsch. So that reacts in one step CO and hydrogen to with the cobalt nanoparticle into fuel, and completely clean fuel also from methane. So this is the actual nanoparticle from the factory. So this is a sample which directly comes from the factory in Qatar. And this is not X-rays, this is electrons. So we did electron microscopy, EELs, and then we colored it. This is the titanium LH, the manganese LH, and the cobalt LH. This is 10 nanometers, so you can see a 10 nanometer sized cobalt nanoparticle, whereas manganese attached to it. So this is nice, but this is an electron microscope, and at that time we could not do the experiment in situ in electron microscopes, and probably it's still at least very challenging to do that today. So we moved to a synchrotron and did X-ray microscopy. So these experiments were initially at ALS. So we used the STIXM. We didn't change anything to the X-ray microscope. We put our nanoreactor in the focal point. The nanoreactor has 2 plates of 50 microns apart, where we move the gases. The spiral is a heater, and then there are holes in the silicon nitride which are only 10 nanometers thick. That looks a little bit over-designed for X-rays, because they can make it thicker. But the nice thing is that the beam damage on the membranes is then minimized, because your membrane is very thin. There's very little heat in the membrane. Then there's the catalyst in between the 2 holes, and you can do your catalysis.
Sorry, Frank, if you're not going to show yields again, I have a question. On L edges of titanium oxide, did you see excitons similar to Zanes?
In EELs? You mean if EELs?
In yields of...
Yeah. The spectrum in EELs is completely identical to X-ray absorption. Yeah.
I just wanted to know about the resolution of this.
Oh, okay. You mean resolution-wise?
Yeah, to make this analysis based on yields.
Yeah. Resolution in EELs is also limited by lifetime now. So they are let's say, for core EELs, yeah, so 0.1 EV energy resolution is available on most. They don't focus so much on core, they focus more on low energy yields. And there the nice development is now the resolution has gone down to less than 10 millielectron volt. So they outcompete RIXS beamlines. Okay, maybe they're slightly okay, but yeah. Yeah, so you get the same information in EELS than in X-rays. So what happens now if you put a sample in a nanoreactor is that this is an example. This is not a catalyst. This is a dust, iron rust, particle. Well, actually, it's a magnetized particle. It's in blue, and then we at 200 nanometer size. So every pixel here, this square is the pixel size of the measurement. And then we heat the sample in hydrogen and reduce it from iron 304 to iron metal. Because this is what we see in every sample, so not only in this reference sample, but in all the catalysts. So if we are somewhere halfway, we always have a situation like this, that some part of the sample is already completely reduced, and the other part, which is 100 nanometers away, is still completely oxidic. So the reduction, at least in these particles, was completely inhomogeneous. Okay, you don't stop there, of course. You completely reduce the nanoparticle, and then on a real Fischer-Tropsch catalyst. Actually, this was a very bad catalyst. So some of the particles were iron. This is in green now. Some were not reduced, so they are still oxidic. But that actually gives us an ideal system to do Fischer-Tropsch and then switch to the carbon KH and look at the nature of carbon at the oxide, at the metal particle, which is this is supposed to do Fischer-Tropsch, and this is an oxide particle, which is probably used to doing something else. So by studying the nature of the carbon spectra, we could correlate the reactions happening on different nanoparticles. Actually, 10 years ago, that didn't really work perfectly yet. So the carbon KHs were a bit, you cannot even see them. Yellow. But later we did some experiments where you can really see different chemical reactions at the center of a catalyst and at the edges of a catalyst. Okay. And then to compare the different advantages and disadvantages of the different sources. So if you have electrons, an electron microscope, your resolution is what you want, so atomic. But your pressure and temperature are a little bit limited. I mean, there are systems where the pressure is higher, but it's difficult, as let's say in standard electron microscopes go above 1 millibar and 300 Celsius. And your sample must be very thin, so less than 300 nanometers. With soft X-rays, the resolution is 5 nanometers. This is an old slide, but I think that's still a valid number. You can go to 1 bar, you can probably now go to 5 bars and a little bit higher temperatures, but still your sample must be very thin, less than 1 micron. So I think for catalysis everybody will, well, most experiments will be done with hard X-rays. Because the resolution is 10 nanometers. You can go to any pressure and any temperature you like, because it's now hard X-rays. And the sample can be macroscopic, so you can do real catalysis.
This is for the open cell, right? But what if you try the same closed cell you used in your Nature paper? What would how would that change?
If you would use that for hard X-rays?
For soft X-rays, electrons, and hard X-rays. Because this is for the open. Or this is for the...
This is for the reactor cell.
Reactor cell.
Yeah.
But electrons, you can put atmospheric pressure there, right? So you put 1 millibar because it's environmental TM. You're talking
Yeah, but what do you mean you can put 1 bar?
No, I mean in your microcell on the Nature paper, you can in principle run atmospheric pressure.
Yes.
And that would change the...
Yeah, okay, that's true. If that would work, then you can put 1 bar electron. Yes, there are special solutions also. Okay, but it's more difficult to keep a stable reactor cell for electrons than for soft X-rays. Okay, so if you work with hard X-rays, till now we have only seen soft X-rays, so now I switch to hard X-rays. A quick thing on metal KHs. And metal K edges, you interpret the spectrum again with excitons and edges. Now the interesting thing is that the edge is a quadrupole in transition metals and rares, and the exciton is quadrupole and the edge is dipole. And the quadrupole is 1,000 times weaker, so this peak goes down by a factor of 1,000, so it's much smaller, and that's the pre-edges in your K edge, metal K edge. So now your spectrum looks like this. So you have your edge excitation, and the edge position depends on valency. So these are two iron 3 systems. This is an iron 2 system. So shift by number of electron volts. And this is your pre-edge region where you have your multiplet spectrum again. So your 1s3d quadrupole excitations. And the intensity is now mainly given by the symmetry. So the tetrahedral is because the break inversion symmetry is much higher than the octahedral wave inversion symmetry. So if you want to do quantitative calculations on this spectrum, then we face some new problems, different from soft X-rays. So the pre-edge itself is easy because it's the same as L-edge. You do a multiplet calculation on your pre-edge, so I just do D4, D5, D6, D7. And then you compare your multiplet calculation with your pre-edge spectrum. People working in the hard X-ray range realize that this is not a normal pre-edge, because then you will not see this fine detail. This is a higher energy resolution fluorescence detected spectrum where you can see all the fine details of your pre-edge, and then you can compare that with the multiplet calculation. Again, you can do the multiplet calculation because it's a self-screen process, and you can, in first approximation, do D5 to 1s1 3d6, and that works. Now to the edge. The K edges are normally calculated by transitions to empty states, so by density functional calculation. This is a calculation we did for lithium cobalt oxide, and if you compare the experiments, so this is normal X-ray absorption, high resolution X-ray absorption, and this is the calculation with whole lifetime adapted to the high resolution one. You get quite reasonable description of all the features and the calculation coming back in the experiment. But the question is this conceptually correct? No, because I asked
Just a quick clarification in your notation. The plus Q means you've put in an estimate of the quadrupole matrix element?
No.
Something else?
Yeah. LDA plus U is the density functional code, and this is the Koch-Hole potential. So we put in the Koch-Hole.
Got it. And back.
Yeah, we put in the quadrupole. Now we do separate calculations. We do quadrupole. We do for the pre-edge. We do with multiplets, and the dipole we do for the edge. We do not mix it.
And just to go back to the partial versus full core hole, what's the choice here?
This is full core hole.
Okay.
But then the question is, should this be the correct way of calculating a K-edge? And then I come back to this graph again, but now instead of doing X-ray absorption photoemission, I put here one as X-ray absorption pre-edge, and then you do a quadrupole excitation directly to the D-band, so this is a self-screened process again, so you can do multiple calculations. If you go to the edge, you excite the 1s electron to a p electron, which I assume to be the same as a free electron. So your D5 goes to 1s1 3d5, but the D6 ligand hole goes now down by the Koch-Hole potential. So now you have two configurations, at least two configurations, which are important for your calculation. So which one should you take when you do your DFT calculation? And that's not obvious. Normally you take this one, it's a full Koch-Hole calculation, but then you neglect this satellite in the X-ray absorption calculation. So is this important?
Or you get an adequate representation of it just from the effect of forming bands in the final states.
Yeah, okay, I'll come to that point later. So this to show you that it's an important, depends on what kind of level of accuracy you like, if it's important or not. This is a 1S photomission, so on iron oxide, and then you see directly the different screening processes. So this is the well-screened peak. So that's the, and then you have satellite 1 and satellite 2, and they come from all the different screening channels. So the mostly screened peak. So now I do four different configurations. So D5, 6, 7, and 8 with leaking holes, and then in the final state I do all the energetics, and then the wet screen peak is core hole D6 leaking hole. So that's this one. So that's where you do your normal fully screen your DFT calculation on. But then you miss these two satellites. So these are effectively electrons with different energies, which you create with the photon. So the photon creates this electron, but it also creates electrons with different energies, and you have to do the electron scattering of the different energies from a single photon energy in your Excel calculation. So is this important? It is important for strongly correlated oxides, like iron oxide, and certainly for rare earths. If you go to high valency, almost everything becomes to the main peak, and you have no satellites. If you do, silver, gold, things like that, then there are no satellites, so then you can forget about it.
I'm sorry, I'm a little confused. This is XPS or XS?
Yeah, this is XPS because I wanted to show the
different thing. Fine.
screening. Yeah,
Thanks.
yeah. Surprisingly, nobody ever publishes XPS, 1S XPS spectra. So because of that, in the last 10 years I collected a lot of different 1S XPS spectra. So now we are writing a systematic paper on 1S XPS of traditional oxide. So took a long time, but and then you see all these satellites and all that. So this is the result of this is that you should convolute your X-ray absorption calculation from FEF, for example, let's say from a density function with this photoemission spectrum. So the convolution of those two spectra will give you a more exact description of X-ray absorption. It's in principle included in FEF because this is in the language of Joshua Kass and John Weir, the particle hole cumulant approach for inelastic losses. That's exactly this process. So in principle, in the FEF9 of you can include this process. Okay. So how I'm doing with time? So I'm going a bit too slow for. So 10 minutes?
Yeah.
Yeah. So I will skip most of the resonant inelastic X-ray scattering, but I want to show some of the interesting aspects. Maybe I'll focus more on the didactical part, and then if you're interested in our latest experiments, then you can ask me afterwards to do that. So now I'm going in the second step to use a core level to look at low energy excitation. So you go from your ground state to a core excited state. And then you go back to an electronic excitation, DD excitation or charge transfer, or you go to a magnon or phonon. So this is around 1 electron volt. This is around 10 millielectron volt, 10 to 100 millielectron volt, depending a little bit on the resolution of your beamline. So the beamline here will have 10 millielectron volt potentially. So then you can really study everything. So this is an example on cobalt oxide. You go to that peak in X-ray absorption, and then you measure your RIXS, and this essentially is the optical spectrum. So this is the elastic line. This is the DD excitation. These are all the DD excitations. Charge transfer excitations are not visible now because they are so strong in optics because the DD excitations are dipole forbidden, but now everything is dipole allowed. So you only see DD excitations in your spectrum. Yeah, so the experiment works like this. So you do your normal X-ray absorption on the sample, and then you have your RIXS detector. So you start from the ground state, you go to a core excited state, and go back to the elastic scattering or the inelastic losses. And you solve everything with Kramer's Heisenberg equation. So you calculate the X-ray absorption from the ground state to the intermediate state, and then from the intermediate state to the final state, dipole or particle, and then include interference effects and broadenings, and then you get your RIXS spectrum. I skipped this, and this is a beamline where we do all the experiments. This is in NSRRC. So it's a 30 millielectron volt resolution beamline. This is a very old slide again, because I think the old slides are interesting to show. So 20 years ago, in 1998, I worked as a postdoc in Groningen, in a group of George Sawatsky, and George asked me, so it's nice, all the X-ray absorption calculations, but what can we do with RIXS, and what happens if you include super exchange interaction? So I started calculating that. So at that time, so the resolution of RIXS was 500 millielectron volts. So this was a completely academic exercise. This blue thing is the X-ray absorption spectrum. If you excite at the main peak of X-ray absorption, and these are the energy loss spectra, you see the elastic line, and you see the DD transition. So that was known, of course, also experimentally. So nothing very interesting. But if you excite at the satellite, you see now the DD transition, the elastic line, the DD transition, and here the other higher multiplet calculations, DD transitions. But you see a new peak at 250 millielectron volt, which is not visible there. And this is we call it spin flip transition, or nowadays the Magnum transition. So why is it visible there and not there? So if your ground state is a triplet, in the intermediate state, the main peak in X-ray absorption is a triplet. So that means that the spin of the core is parallel to the spin of the valence hole. But the satellite is a singlet. So the satellite has a singlet state of the core hole spin and the valence spin. And that means that that satellite doesn't have any memory of where it comes from. So it can go back to the ground state, or it can go back to a state where it flips both spins. So you have now suddenly 2 spins down instead of 2 spins up. And that gives the super exchange energy and the Magnum peak. And this peak, of course, has dispersion, which this is a local calculation, which we did not include. Although that dispersion is still smaller than 10 millielectron volts, so you cannot detect it even with the best machines. Yeah. So this gives us a lot of new experiments. With X-ray absorption, you are in the electron volt range, so you can study electron-electron interactions, crystal field effects and charge transfer effects, or chemical bonding effects and charge transfer effects, screening effects. So that's typically done with X-ray absorption. But now we can go to millielectron volts. So I put 30, but okay, nowadays I think ESRF is 25, and it'll be better maybe soon. But let's say 30, you can do study spin-orbit excitations, magnetic excitations, distortions, and vibrations. So you go to a completely new set of excitations. The situation regarding dichroisms and angular dependence becomes now even more complicated than before. Before it was already tricky because you have photon in and sample, but now you have photon in, sample, and photon out. And you have polarizations. And that gives you millions of different options which have to be discovered for the possible applications you can get. Maybe I'll skip some examples. This is maybe something I like to show because this is a nice example. So one study we did was on Ruby. And from our point of view, that was not because it's a nice color, but because it's a very simple system. It's a chromium impurity in alumina, so you can approximate it almost perfectly as a single chromium atom in an innocent oxygen host. And then we did the RIXS experiments. And then I want to show some analysis of the RIXS. So this is the X-ray absorption, chromium LH, and you cannot see the difference between theory and experiment now. But it's perfect on this. This is these are the RIXS spectra excited at these arrows. So we were not very intelligent. We just took 1 electron volt steps in the address beamline. And this is the optical spectrum. So the optical spectrum has a dipole allowed transitions, and you can see that they come back at excitation D. So if you excite there, you get the spin allowed transition. And now you can analyze these RIXS spectra from semi-empirical calculations, and then you can see that if you look at this peak, that's the first peak in optics. That's the spin allowed transition, this one. And spin allowed transitions do not change if you change the Slate integral, so the Rocca parameter. So this is Rocca parameter B and Rocca parameter C, so the electron-electron interactions. But the energy of that peak is completely insensitive to any of the electron-electron interactions. So that means you can optimize the crystal field splitting directly from the position of this peak in optics of that peak. So now you can do it at least in 2 digits. Maybe you can even do it in 3 digits, but let's say 2.32 electron volts. It's also the ground state value instead of the final state value. Now you can see here that the other dipole allowed transitions in pink, they also do not move with Rocca parameter C, so you can fix them from this peak. And that gives you Rocca parameter B is 0.071. And now from this spin forbidden transition, which is there, you can now fix the third Rocca parameter C. So you get the 3 parameters determining the spectral shape in 3 digits directly from your RIXS spectrum. This would be completely impossible from X-ray absorption. So I call this a multiple challenge because I give this challenge to the theoreticians to calculate from first principles. Because it's extremely difficult, because this ratio between the Rocca parameter C and B, or the ratio between Slate integrals F2 and F4, is completely different from an atom. So the solid is completely modifying the electron-electron interactions. So, and then as a last example is the spin state in lanthanum cobalt oxide. It's a very old problem again. There are 3 possible ground states: low spin, high spin, and intermediate spin, and that is the orientation of the states. Here, just a reminder, so the term symbols I indicate here and the orbital occupations are just indications. The real ground state is a linear combination of everything, and will be always a mixture between the different spin states. In a solid, I mean, you never get 100% pure singlet A1, it's always a few percent of other states. But let's say we start with this description. At 0 Kelvin, a single crystal of lanthanum cobalt oxide will be low spin. And if you heat up at above 300 Celsius, it will be high spin. That's known. So what the reason that I put the intermediate spin? I quickly go through the experiments. So just if you do those experiments on solids, this is the RIXS graph. This is 0 is the peak position of the L3, and this is the energy loss. And here you see that this large blob, and that's fluorescence. So that's not something we like to analyze. So we then, if we did the temperature-dependent experiments, we not go to the maximum of the L3 because then we see mainly fluorescence, but we go a little bit before. So somewhere here. So if you make a cut here, you don't have fluorescence and you still have your DP excitations. And then we heat up, and then you can see the low spin, high spin transition point. That's interesting, but you can read that back in the paper. But that's not the whole story, because this is the energetics now. So you have low spin at low temperature, and then it switches to high spin at high temperature. But there's also intermediate spin, and that's relatively close. It's 0.2 or 0.3 electron volt away. And the intermediate spin can hop very strongly and can couple to the low spin. So you have very strong T2G and EG hopping between sites which are low spin and intermediate spin. So if you want to study the dynamics of the electron transfer in the system, you can never switch from low spin to high spin. So they are islands separate in the system, but you can hop from low spin to intermediate spin. If this dispersion of this intermediate state becomes very large, and some parts in reciprocal space it can fall below the low spin, and then you have an excitonic insulator. It's nice. It's a hot topic in if you're not in this field. But so we did some calculations. So actually, this is now calculations from Atsushi Hariki. So we analyzed the data. I will skip that part, but I will show this graph. This is the density of states of lanthanum cobalt oxide. But you see here energy loss. So this is not the normal density of states, but this is the density of electron hole excitations as a function of momentum in the single crystal. This is the density of states. This is multiplied by matrix elements, so that's the RIXS, so that's what we expect. And then this is folded out, so this is what you think of it as a band structure. but this is again not a real band structure, it's the electron hole excitations. And now you see here between 0 and 0.1, that's the low spin and the high spin state. So they are essentially horizontal because they do not couple, they are essentially atomic states. But this is the intermediate state, intermediate spin state. So this has a very large dispersion. It's between 0.6 and 0.2. So it doesn't really touch 0, but you can see here that it starts to mix. So here the ground state becomes a mixture between low spin and intermediate. These are the 4 data points. Every data point took 24 hours on the address beamline and Swiss light source. So this was a whole week of beam time. These 4 points. So this would be an ideal experiment to repeat with better resolution. This initial experiment was with 100 millielectron volt. We repeated it now with 30 millielectron volt at ESRF. But it's a nice tool. So okay, this is very well known in cuprates, and then you have the magnons and the things. But you can also now start to think of doing that in open shell systems. Okay. That's what I wanted to tell. Sorry, I skipped some things. So the work was done by the group in Utrecht, the PhD students and the postdocs. The RIXS we do in Swiss light source, and actually 90% we do in Taiwan and in Spring 8. And actually I forgot the ESRF ID2. Theory, I collaborate with Maurits Haverkort in Heidelberg and Robert Green in he recently moved from Vancouver to Saskatoon. And the last calculations were by Tsushi Hariki in Vienna. And the samples were a collaboration with Pietro Gambardella on the adsorbates and thin film samples we always make in Twente. And thank you for your attention.
Questions? Right.
I'd like to take you back to the slide with the Rocca parameters. You don't actually have to go back to the slide, but conceptually, you commented that the B and C parameters, or in the other notation F2 and F4, are different in the solid than in the atom. But I think we both will recall that this is not conventional wisdom.
No.
We usually say that F0, which is the primary U parameter, is screened in solids, but F2 and F4 are carried over from the atom and they are quote-unquote unscreened. So is your results in this regard, they're obviously different from conventional wisdom.
Yeah.
Should I see them as sort of a new thing that's still being digested, or is there sort of a ready explanation?
Yeah, I think that we should, before we could not really think about it because we had not experimental...
Yeah, direct measurement wasn't so feasible, in other words.
Yeah.
So conventional wisdom was convenient, right?
Yeah, yes. Convenient and maybe also enough, because for X-ray absorption I think it's probably enough to use that rule. And the second thing is Ruby is not the normal system. It's a very... so the electric... I mean the local site is very low symmetry, and that's the ideal case for this non-conventional ratio to happen.
Yeah.
So probably many simple oxides like nickel oxide, that's also well, then it's exactly very close to the normal ratio. So I think that there are oxides where it's a normal ratio and there are oxides where it's a non-normal ratio. And the non-normal ratio oxides might be very interesting from a color point of view, which is the important thing in Ruby, but also in luminescence. And so those systems are, this is my prediction, that luminescent systems, then you would probably be far away from the normal reduction. Octahedral oxides will be fine.
I get your logic, that's interesting.
Yeah.
Well, I can't resist just one other quick point. The last topic with the excitonic insulator, I mean, that's obviously really new and really cool.
Yeah.
So I guess the next experiments, you're going to go down and find that place where the intermediate spin state's really coming down, right?
Yeah, yeah.
Just to say.
Yeah. Actually, to say we tried that already. And,
Oh, I see.
but it didn't work.
Sends the theorist back to the drawing board, maybe.
Yeah, the theorist So Jan Kuges and Susie are now working on the data, but it looks like it's a little bit more complicated than the initial calculation, because this was data with 100 millielectron volt, and that seemed ideal for their, because we took the data and they did calculations and it fitted perfectly. But now with the high resolution data, it's less perfect. There is, although they are kind of first principle calculation, there's still the Hubbard U, which is not first principle, and that can modify things. That actually will.
To the other conversation also.
Yeah.
With the F2 and F4, I don't know. Not
yes.
obvious to me, but
Yeah. Actually, the Hubbard U determines actually if you have an excitonic insulator or not.
At the zeroth order, right?
All right, well, if there are no more questions, let's thank Frank for being here. Give him a good applause.